just a couple of things I want to talk about right quick before we start doing the notes. For lab on Monday, you'll go into the course content on Blackboard, I remember my organization, course content, and then there's a folder called lab, and inside the lab, there'll be a folder for Monday. There'll be a lab handout, which you'll need to open and print and bring to lab. The first lab we're doing next week is going to be using some equipment, but it's to gain a statistical data set. So some of the equipment you've certainly used before. In fact, there's probably nothing you haven't used. You may not have used the analytical balances, 4 decimal place, which are a staple instrument that we use, and you may not use the burette the way that we're using. But things like pipettes, everything else you graduate cylinders, you certainly have experience with. So try to read over that, but certainly, especially if you're printing from home, print it out. It will be up by noon today. There'll be the printout, and then there'll be another icon in there, and the other icons where you actually submit your lab report. And it's a Word document. So we'll talk about that more as we get into it next week on the report process. Okay, we're going to continue and finish chapter 0 and go back and look at the concepts of this, and we'll go ahead and roll right into chapter 1. The last thing that we were talking about was this idea of calibration curves, and we have linear lines. The key thing we need to start thinking about is that with a calibration, we're looking at whatever our instrument response is. Okay, in this example, it's peak height, it could be peak area, it could be current, it may be temperature. There are a lot of different ways that we could have a variable that we could measure as a function of analyte concentration. But when you create the calibration curve, the important thing is you put the concentration on the x-axis and your signal from the instrument or measured response is going to go on the y-axis. So that takes us to where we are at the end where we didn't quite finish up. So I'm going to jump over that last slide and we'll work this. We went through that one. Let's do this last example. It says a calibration curve is determined for aspirin and is made from known concentrations. The concentrations are milligrams per milliliter. So that means that's going to be the units that we're going to have for concentration. And it says if the equation to the line is this peak area equals some number times concentration minus something. What's the concentration if the unknown has a peak area of 85 or 83.5? So key thing to realize this is just thinking about what we've got. So this is an equation. Y equals mx plus b, and that's a critical way to think about it. So this is the slope. X is going to be the concentration, and we've got the y-intercept. So effectively what we have is peak area, PA, versus concentration, and then we've got this equation our line that describes that. We've got the equation for the line. So what we have is that the peak area over here is some value 83.5, and we're going to find out what's the concentration is. So the way that we're going to do it mathematically is simply substitute this in for the y value. So the way we're going to solve it is 83.5 equals the 12.565 times concentration. So you're just doing the math to isolate what is the concentration term. That's what we're looking for. So the 83.5. And this is a minus on this side, so we're going to take the other side, so we're going to make it a plus. All right, so we're trying to isolate the concentration term. So that means we're going to divide this now. Okay, so that's our equation we're going to use to rearrange that. Yep. And I got 6.7 milligrams per milliliter. Okay. We're going to talk about as we go further about how many significant figures that's coming up in a chapter pretty soon. We're going to talk about that in painful detail, as you'll find out, but understand how we got that. So the key thing is just realizing these equations are simply describing this relationship. What is the relationship between this signal that was obtained for known standards? That's how the calibration curve is generated. Once we know that relationship, this equation, all we need to do is plug in y for an unknown and solve for x. Okay, so that's simply what we're doing when we do a traditional linear calibration. Now, unfortunately, they're not all linear, and they're not all that straightforward. But we start with the simple, and then we're going to build upon that. Okay, so that concludes the key things we're going to talk about in Chapter 0, which is really just an introduction. So we're going to go ahead and go into Chapter 1. So Chapter 1 fundamentally is a review chapter. There will be very few things, if any, in here that you haven't seen in your freshman chemistry book. Okay, and I'll say that they were in your freshman chemistry book. The detail that your instructor emphasized, things like parts per million, some different units of concentration, are vary a little bit. We all teach it a little bit differently and have different opinions of what are the key aspects. But there's a review in the metric system. You've seen that in the videos. It's just something we have to be comfortable with. And the process of converting between units called using dimensional analysis or factor analysis, everybody was taught that in science courses, certainly in freshman chemistry to some degree. Some faculty may not insist that you apply that. I do. Okay, there's just too many opportunities to screw things up. And I see a number of students come through this class that don't have a solid foundation in how to do that. If you haven't got that clear understanding yet, I want you to accomplish that before the semester is over with. We're going to talk about a lot of different ways of changing concentration or different expressions of concentration, and more importantly, how to convert between concentrations, how to go between things like molarity and parts per million or density or whatever. We need to be able to go to, once we know the form of concentration or determine that, we need to be able to go to anything else, whatever it may be. All right, we're going to talk a little bit about making some solutions up and using the dilution equations. We'll talk a little bit about some stoichiometry, which we learned in Gen Chem, you learned in organic, doing percent yields and stuff, but we're going to do a couple of applications to gravimetric analysis in particular. So one of the things that I just want to point out that's, and I don't remember if I did that in the video last year or not, the problems that are at the end of the chapter, and it varies with the chapter, there's typically 6 to 8, in some chapters up to 10 problems. There's a set of problems right at the end, or the start of the end of the chapter, called exercise. And the exercise problems have complete solutions in the appendix. And that's something new that this version of the textbook just added last year. So it's not just here's the answer. All the answers to the problem are in the back of the book. Okay, so just the answers themselves, but these have step-by-step. This is how you set it up and work it out. So that's somebody had asked about a study guide. I would encourage you, instead of trying to come up, or not a study guide, a solutions manual. If you want to hunt one of those down, I don't have an ISBN number for it. I don't see one on the website that there is one, but this exercise thing is pretty close to that. So it at least shows you completely how to work out that particular type of problem. Some problems to look at. The thing I would tell you is that this is our basis for the rest of the semester. This is the one chapter. I'm going to give you a homework assignment, and I'll post it on Blackboard today. When I get it up, I'll send you an email that it's ready and available for you to do. I'm going to give you like 8 to 10 problems to do. These types of problems. It'll be a week to work on it. You can work with somebody. I know you're going to turn in your own paper, but they don't encourage you. If you don't figure out how to do it yourself, it's not going to be a benefit to you. And I'm going to expect and demand that you do this all through the semester. We just have to have a solid foundation to be able to convert do factor analysis, convert between units. So if you had freshman chem a long time ago, or you had a weak experience when you did it and this stuff seems foreign to you, the thing I'll encourage you to do is to spend the effort in this chapter, because if you don't, you're going to be lost a lot of the semester, because we're going to be just clicking through this stuff once we get the foundation. If you don't have a Gen Chem book anymore and you want to review some stuff, there's about a dozen Gen Chem books down 214. They're older editions. They're different authors. You probably can find the textbook that you took. You won't pull it off the shelf and use it to review down there. All right. We discourage students from taking them home, but if you need to take one home for the weekend, take it home for the weekend, just bring it back. Okay? That's the thing I encourage you to do. And if you, I've got books that I'll loan you that are editions we didn't use in my office if you still need something else.
Dr. Smith?
Yes?
Will that homework assignment be problems out of the text?
No.
Oh.
No, it's a sheet that I'm making up.
Okay.
It's 3 more problems I'm making up. So, nope. Okay. So, and I emphasize this in the videos, and I really want to just go over that again. Whatever calculator you choose, it needs to be a scientific calculator that has statistics functions on it. There are a lot of different types of options that you have. I tell you, you don't need to spend more than $15 on a calculator. And there's tons of them. The thing that you need to do is you need to find a manual to go with your calculator, unless you're that familiar with it. You need to understand how to do things like standard deviations, summations, memory. There are much more complicated calculators than this old guy that I use. You just need to pick a calculator and go with it so that you can do all the functions and calculations. Things like order of entry. So if you want to take a log of a number, some calculators you can put the number in, and this one you can put the number in and just hit the log button. It takes the log. Different versions of the same TI-30, you have to hit the log and the parentheses open up, then you put the number in, so you have to know in advance what you're doing sometimes. So you just have to choose the calculator and understand how it works. There's no right or wrong calculator. As long as it's a scientific calculator, all of them are going to be able to do the same things. Some of them will do XY regressions for you, so they'll actually let you put in an X and a Y data set and calculate those simultaneously. There's some advantages to that. You'll learn about it in the next chapter when we learn about linear regression, but it's not a necessity by any means to have that. So you just do 2 sets of calculations, individual calculations with an old calculator like this instead of doing them both simultaneously. So I'll try to help you learn your calculators from what I know, but for the most part, if I don't know it, it's going to be your responsibility to. And the thing I'll tell you on your calculators, you can watch a YouTube video, and some 12-year-olds will show you how to do it because they love to make YouTube videos. Okay, so which of the following is not an SI unit? This is one of the things that I went over in the videos. So one of those is not a standard metric unit. They should be 11. Yeah, there we go. Okay, so we said, everybody said A. Okay. So what do we think? It is it's a gram. So a gram is the only thing that's not a standard thing that's based on the amount of mass is based on what? What's the SI unit for mass? It's a kilogram. It's based on a liter of water. That's what the French set it up with. It's a 10 centimeter by 10 centimeter cube of water. And they took the mass of it. They made a plutonium iridium copy of it that weighed exactly the same mass. Every country got a copy of that. There's some mystery going on with those that we really don't understand as much because the idea is that we think that's one of the most stable alloys that we know. It's resistant to It's resistant, very resistant to corrosion. They've been kept in an inert environment. We hadn't broken ours out for a long time, but some countries have taken theirs out and started trying to do mass comparisons, and they seem to be losing mass. We thought they'd be gaining mass from oxygen on the surface, if anything. But some countries, their mass seems to be decreasing. Other countries are increasing. When I'm saying this, you're talking about going out to 8 decimal points. But the problem we still have with it is it's a physical, tangible object. I mean, if somehow when they touch it, they scrape a little metal off the surface, it doesn't weigh what it used to. And we're still referencing back to that tangible thing. So we're going to have to, somewhere in the future, come up with a different way of determining what mass is going to be. All right, so again, I went over the units in the videos. Certainly, the thing that we'll use the most is kilograms. Convert that to amount of a substance into moles. We don't do a lot of temperature calculations. The only place that's going to come into role is when we get into thermodynamics for equilibrium calculations to any great extent. The thing you do need to be comfortable with are the metric system, and in particular, the common units. Some of the things that we may not even heard of these things. You may not have heard of yattas and zettas. Those are what we use to describe very, very small amounts of stuff. So we've got on the extreme sides, so let's start in the center. Your base unit is going to be whatever it is. A deca is 1. So it's 10 times whatever it is. I've never used hecto in anything. It has its purposes, but kilos, 10 to the third, you should know that. Mega, capital M, 10 to the sixth. The other ones we don't use that much unless you're talking about things like frequency. And we'll do a little bit of that as the semester going on. Where we start using some of these extreme ones is we use them as multipliers when we're talking about small amounts of material. So going to the very small, so centa, we use that for a unit of measurement. Milli, we use that for volume all the time, milliliters. Micros, we use that. And then we start talking about the smaller things, like the volume of a cell is going to be nanoliters. All right? We start talking about picos, picomoles, femtomoles. That may be how much of a material is inside of a single cell. Right? And then when you start talking about things that are there at very low copies, we start using the attos and zeptos. In terms of technology now, we're down to the yoctomoles. The ultimate sensitivity that you have of any piece of instrumentation is to detect a single molecule in whatever volume that is. And we have instruments today that can do that. We can see a single copy of something with laser-induced fluorescence. And there's other techniques that are starting to gain that sensitivity. That's ultimate sensitivity. So if you have that 1 mole in a liter, okay, you're going to be in the yoctomolar range. That's just something you don't talk about that much because it seems like such a small volume. But we have a laser-induced fluorometer that can see 100 copies. So I mean, we're in the high yoctomole range. So zeptomolar, and that's really when you start seeing sensitivity that great, it's almost unimaginable how much small material can be diluted into a large volume and you still be in that concentration rate. So when you start looking at that low level, you start to see a lot of different material. Okay, just the conversions that you need to be familiar with. I went over on the videos the difference between mass and weight. Again, the term that we use and base our chemistry on is mass, even though we're measuring weight, the force in the lab, but we have a conversion that we can deal with, no problem. The key thing that I want you to be able to do is to be able to apply this dimensional analysis or factor analysis. And again, the goal of that is to be able to convert units from one form to the other. You set up conversion factors. That's each step so that you get the units to cancel out. When you set the problem up, if your units don't cancel out, don't even break the calculator out. Because if you don't end up with a unit that you want left on top, or in some cases, you're going to have units on top and bottom. You're not there. Okay, and it's real easy to mix things up, but it's a simple correction if you do your factor analysis. So, just the first one that we for a quick example. And there may be a couple of things that I repeated here that were in the videos, but I just want to give you an opportunity to ask questions for this this first portion of it. So on this one, it's a speed, 3.45 meters per second. And I'm going to do two conversions. I want to take meters into kilometers on top. And on the bottom of the unit, I want to take the unit of time in seconds and go to hours. All right, so if you don't remember your units that well, we're going to build upon that. To go from meters to kilometers, what I'm going to put is the unit I want to cancel out on the bottom, and the unit I want to arrive to is going to go on top, so those units are going to cancel out. 1 kilometer is 10 to the third meters. Okay, so if I do that simple step, what it's going to do is allow meters to cancel out. I keep the math terms, the numerical values, and make kilometers. Now I'm going to do a similar thing with time. So there are 60 seconds per minute. There are 60 minutes per an hour. In a similar fashion, minutes and minutes cancel out. Seconds and seconds cancel out. All right, what I'm left with are kilometers per an hour. That's the units I'm trying to arrive at. All the other units have cancel out. Now, the numerical terms, I still have to multiply through. So to find out what that's going to be, I'm going to do all these. So I've got to take the 3.45 times 60 times 60 divided by 1,000. And I get 12.42 kilometers per an hour. And I need to go to 3 significant figures, so I would lose that last digit off. So I'd say it is 12.4. We'll talk about significant figures as we go. Anybody have a question on that? I'll set that up. Straightforward enough? Okay. That's the process of dimensional analysis or factor analysis. Set up your units in these conversion ratios or conversion factors so that you cancel out the unit you have. The key thing is just finding out what's the relationship between those two variables, kilometers to meters. And if you wanted to take this one and you wanted to do it in a single step and say, okay, there are 3,600 seconds per an hour, absolutely nothing wrong with that. If you know that, there's you can shorten it or simplify it if you choose. Okay, so here's a simple one for you to do. Here I want you to take a small number of kilograms and convert it to micrograms. And the hint I'll give you is always go back to the base unit. Go to grams as intermediate, and then copy over. If you can see it in your head in one step, okay. more answers. Last 3. I see a countdown clock coming in our future. It should be really easy to you. Last chance. All right. We have some diversity in our answers. There is a predominant answer. More than half the class chose D, but the 45% of the class chose other topics. So let's figure out what it should be. So setting this particular problem up, start with what you have, and it's a small number. It's to the -7th power of kilograms. Go back to the base unit. So 1 kilogram is 10 to the 3rd grams. Then go from the unit you have. 1 gram is 10 to the 6th micrograms. All right, check my units out, see what cancels. Grams and grams cancel. Kilograms and kilograms cancel. Just doing the calculation in my head. So I've got 10 to the 3rd times 10 to the 6th, that's 10 to the 9th. So I've got 10 to the -7th times 10 to the 9th, that's going to cancel out and give me 10 to the 2. So 123 times 10 to the 2, I'm going to move the decimal place over 2 to the right. 123 micrograms, what I expect to see. That's indeed the answer. So, more than half of you are on track. If you weren't one of those, this is something you got to work on. That should be straightforward for you. Learn how to, I'll give you this table on the first test, but the things like going from kilograms, and the common things we do is we switch them. All right, that's just something as you learn how to read the tables and plug them into the dimensional analysis, you can get that straightened out, but it takes effort on your part. Okay? Questions on that before we go on? All right. So that's factor analysis, dimensional analysis. We'll use it constantly this semester. Okay, I want to talk about, even though I went over this in the video, I want to just mention it briefly and give you an opportunity to ask questions if you have them here. So, concentration is any form of an expression of how much of a substance is in a given volume or mass. So, it can be mass, volume. It can be however we want to do it. One of the things that we talked about in the chapter 0 is getting results into the form that the person we're doing the test for understands. And a lot of times that doesn't involve using moles. We can explain something in percent to a non-chemist, but a lot of times we collect data in terms of moles and we have to convert that into something else. Whenever we describe making up mixtures and solutions, we use the term solute and solvent. That was something was introduced to you in general chemistry. And those simply mean the minor and major components in a homogeneous solutions. If we think about the units of concentration that we will use, molarity, capital M, is something we'll use constantly throughout this semester. Formality is a deviation of molarity where it looks at the number of equivalences per mole. All right, so if you're looking at the number of protons that are giving off with a monoprotic acid, molarity and formality are equivalent. But if it were something like sulfuric acid, where there are 2 protons per mole, the formality would be 2 times the molar concentration. That's explained in the textbook. Formality is pretty much a forgotten term. We kind of went to molarity now. The problem is that some of the people that write these standardized exams are forgotten. we learned, when we learned our chemistry and fundamentals, some of the people are a little bit older than me that are still writing these tests. Formality was an important term if you were educated in the 60s and 70s. So they may emphasize it more than that's in the textbooks today. Molality is one that's important for us. Lowercase m, it's moles per kilogram of solvent, and the good thing about molality is that it's temperature independent. So it doesn't change with the density of the solvent. So in an industrial setting, molality is just as common as molarity. Because molarity, if you go into a reactor that you make a solution up at room temperature, and you take that solution and you put it in a reactor now that's 400 degrees, there's going to be a great change in volume. Okay, or if you cool it down, there's going to be a change in volume. To give you an example, when we make a solution up in the lab, and we put it into something like a 1 liter volumetric flask. So you fill it to the mark, it has 1 liter volume at room temperature. If I take that at room temperature, so if it's here at let's say 20 degrees, room temperature, if I take that 1 liter and I put it in the refrigerator and allow it to cool off, what will happen is that volume will decrease a couple of percent. All right, so now at something like 3 degrees Celsius, the volume decreases. Now there's still the same number of moles of whatever the solute that was in here. This is a sealed container, but it's got colder. The molecular motion slowed down. The volume decreases. So did concentration go up or down when that happened? Concentration went up because the volume decreased. Still the same number of moles. So the molar concentration went up. So when this happened, there was an increase in the molarity, but what happens is there's no change in the molality because the mass of the solvent is still there. All the moles of solvent are still there. So molality is something we use, especially in industrial settings, if you're speaking with somebody that's has that background or providing them information. We'll use Avogadro as a number every while. I expect most of you are seniors in here. You should know what Avogadro's number is. So 6.022 times 10 to the 23rd. It's on somebody's shirt. Just look around. I saw it cut 3 or 4 times this week on people's shirts. So it's a big year in chemistry for ACS. All right. The rules that we have with moles, just remember when you've got molar concentration. So, and that's the key thing. It's got to be molar concentration. But that's our most common unit. If it's molar, moles per liter, and if the volume is in liters, and you take those two things together and multiply them out, you get moles. So concentration times volume gives you moles. Make sure that you set the units up to get them to cancel out in the problem. You do dimensional analysis even on something as simple as that. Millimoles, using with milliliters, can save us some time, and it basically saves you a step in your analysis. And if you're going from milliliters to milliliters, you will find out that the millis cancel out. The thing I'll tell you is that until you're comfortable using that, always set your dimensional analysis up. Otherwise, if you forget, your answer is going to be off by a factor of 1,000. And the way I look at doing a problem like that, so if you do the test and you mess up with the milli conversions, I consider the milli conversion one step in the calculation. So maybe out of a 6-point problem, you're going to lose 2. It's not going to kill you on it, but we do need to learn how to do things correctly. Our goal is to get whatever the answer is. Percent compositions. This is the simple way to make things up because all we have to do is determine the mass of a solute and put it into a solution. Sometimes we have to convert back to that when we report something out, and we do it 2 common ways. Percent weight, even though this is the terminology of the textbook, it really should be percent mass. Oops, sorry. Should be percent mass instead of percent weight, but that's these are the author's words, not mine. And we still say weight percent. But the key thing is it's going to be represented by typically grams over grams. We have to show some way what it is. So when you say percent, you're going to put grams over grams, R, you're going to put percent, m, which is mass. All right. We find that there's too many units we have to repeat. Small m, we just said, was molality a second ago. Which one is it? Well, we have to understand what term context it's being used in. Percent volumes, if we're dealing with liquids, we can talk about volume of the solution and volume over volume of the solution. Sometimes we talk about things that are weight volume. So we'll have a percent mass volume. So it's going to have units that are things like grams of solute per volume of solution. There's other combinations you can have. But the key thing to realize is that what it's telling us is simply that ratio. If you say something's 95% ethanol, that means weight. That means there are 95 grams of ethanol per 100 grams of the solution. And the solution contains the solute. The solution is the whole. The solute is the minor component in the system. Okay, here's a term that we haven't used that much. We sometimes mention it in general chemistry, sometimes it's skipped right by, even though the terminology is in the textbook. And the term is specific gravity. And specific gravity essentially is density, but what it is a unitless version of density. Okay, it's the ratio of the density of a substance to the density of water. So it allows you to set it up into whatever units you want. So if you want it in milligrams per liter, you can set it up in milligrams per liter. So that's the essential thing of what specific gravity is it's simply an expression of density, but it allows you to set the units up as you want. And the reason it's an important thing for us to look at, it's the way that we buy a lot of concentrated acids and bases. So if I took any one of these species and I took that substance and extracted the water out of it, so if I took acetic acid and took a bottle of vinegar and boiled it down, would I have acetic acid left? So vinegar, household vinegar is 5% acetic acid, so 95% water. So if I boiled the water off, what would I have left? Well, there's only two components in it, acetic acid and water. If I boil the water off, wouldn't be left with anything. Why? Because every one of these compounds is volatile. The way that these reagents are made is you take that reagent and you bubble it through water. So you can't have pure of any one of these things at atmospheric conditions. So we make saturated solutions of it. So like at the product that we make around here at Valiant, the paper mill is a side product. Sulfur dioxide comes out the paper mill. It comes out the top of the towers. And when I was a kid growing up, I used to hunt in a place called Eagletown. We went down there and camped every deer season, turkey season, just as a trip with friends. But you were new when you went through Hugo and you went through Fort Townsend, depending on the wind blowing, because you started smelling it. It was a strong smell. And because the EPA at that time didn't have the regulations that made the sulfur dioxide be contained. Now they have scrubbers on the towers, and the sulfur dioxide content, you don't even know it's there compared to what I'm familiar with. But the waste product, they track the sulfur dioxide coming out with hydrogen peroxide, and it produces sulfuric acid. So they produce about a train car load of sulfuric acid a day, which was a waste product that they sell off. But that would be a volatile component. You bubble that sulfuric acid into water and you saturate it. Now, it's pretty concentrated. It's 96%. Other things like ammonia are a much lower concentration. Ammonia, you just can't get a lot of it in water and it'll saturate. It's only around 29% by mass. The way that we find out what it is exactly to calculate molar concentration is we measure the specific gravity. We can measure the specific gravity or density to several decimal places using some good volumetric glassware and using a balance that gives us at least 4 significant figures. we can come up with 4 digits of specific gravity that are significant. And that's pretty useful data for us. So here's an example of what we might have to do if I wanted to take that and convert it into molar concentration. So here's the solution of nitric acid. It's got a molar mass. So for the most part, I'm going to consider everybody in here knows how to calculate formula weight and molar masses. So I'm going to give them to you. I don't want you to spend our time on a test doing those. So wherever you see MM or parentheses MM, that means I'm giving you the molar mass for it. There may be an occasion where I want you to do it, but most part I'm going to give those to you. So there's no, if you look at the bottle, there's no mention of what the molarity is in the system. All right, so what we have to do is it tells the solution 68%, and on the stamp somewhere they measured it, the density or the specific gravity has been determined for that lot. So we have to take the combination of those things, and we want to find out what is this molar concentration, because I need to dilute it down and use it as a reagent plant. So if I think about it, what is my concentration that's given here? Something describes the concentration. What is it?
20%.
Okay, this is the concentration. What I need to do is convert that into molarity. Okay, so that's going to be my strategy of what I need to accomplish in my dimensional analysis. All right, so I'm going to take and write that down. So it's 68%. So what that means is there's 68 grams of nitric acid per 100 grams of solution. That's what the 68% means. Percent per parts per 100. Okay, so now I've got to think about that in terms of a strategy. I've got to take my grams of nitric acid. So if I want to go into molarity, I want to be in moles of nitric acid per liter of solution. Okay, so that's where I'm trying to get to. All right, so how would we go from grams to moles of nitric acid? The molar mass, yeah, that's simple. All right, so molar mass is, I give you at 63.01 grams of nitric acid per mole of nitric acid. All right, so that's not too bad. So I can see that those are going to cancel out. I'll go ahead and just mark them out. So I've got moles of nitric acid. That's what I want. So that's good. All right, so now how about this next step? How do I go from grams of solution to liters of solution? Use the density. Okay, so the density is given as 1.5129 grams of solution per milliliter, and then I can convert from milliliters to liters. Milliliters and milliliters cancel out, grams of solution cancel out. I'm left with moles per liter, which is where I'm trying to get. That tells me I've got the problem set up right. At that point, I'm going to calculate. Okay, so I'm not going to even mess with it before that until I see the calculation come out. So 68, 9.
Count the 68 as a significant figure, do you? Okay.
Well, you're going to have to use it up here. So there's 3. A lot of times I'll be lazy in a problem, and I won't write them, but I'm always going to go back and look at the provided information on my result. And we're going to talk about that when we get to the chapter on statistics. All right, I got a number. Anybody else get that? Okay. Let's just, it's conversion of units. It's getting from what's provided to where we want to go. That's a common example of one of the things we need to do. All right, any questions on that? Maybe you can guess what's next. Your turn. So here you've got perchloric acid. It's 70% by weight. I give you the molar mass. I give you its specific gravity or density. And I want you to calculate the molarity. No, still a couple more. Last one. Yeah, we're all in. Let's see what we got. So, majority of you think it's 82% says it's answer B. Let's just set it up right quick. All right, so start with what we know. The mass of the perchloric acid for the mass of the solution. Convert the perchloric acid to moles. Convert the grams of solution to milliliters using density. And then can finally convert from milliliters to liters. I'm going to check my units before I do anything else. Milliliters and milliliters cancel solution. Grams of solution, grams of solution, grams of perchloric acid, grams of perchloric acid. I'm left with moles per liter. That's molarity. That's what I want. So if I put my numbers in, I'll find out that indeed it's 11.6. So most of you are on track there. All right. The thing I encourage you to do is you'll need to watch the last two videos for this chapter. We'll finish up this chapter on Monday. But this is, you're kind of, when you see this problem, I encourage you to start working on the problem. I haven't looked at it today. But if you find out you're weak on trying to work these and you don't understand, spend 10 or 15 hours this week, upcoming week, work these problems, get that foundation reset in your mind. Some of you hadn't had general chemistry in 3 years. Okay, and you may not have done some of these calculations in a while. Some of you it may have been longer than that. So refresh get ready to do the problems, because the convergence of units is a lot of it this semester. We gotta have a foundation on it. Okay, have a good weekend. Remember to print that lab on Monday.
It says the one where it's calculated.
Oh, yeah, that was way so.
Okay, like, I don't understand how it flipped off. I got everything but that. I have a quick question on the when you did the Parks Pavilion
Okay.
on the video.
Yeah, let me stop this.